Last time we discussed the carrier concentration and conduction in intrinsic semiconductors, but the crucial thing about semiconductors is the possibility to precisely control the carrier concentrations through controlled doping of a very pure sample of semiconductor. In other words, the entire interest from the point of view of devices and semiconductor electronics is based on the fact that there exist extrinsic semiconductors as contrasted with intrinsic semiconductors, which we discussed last time. We will discuss the carrier transport in an extrinsic semiconductor in this lecture. It has already been mentioned that an extrinsic semiconductor is one in which a semiconductor which is extremely pure is doped with donor or acceptor impurities in controlled amounts. For example, a sample of silicon is doped with an impurity like phosphorus, arsenic, etc., to give a donor impurity which modifies the behavior of the semiconductor completely and which gives the possibility to control this behavior and use it in various kinds of physical situations. So, similarly, there can be acceptor impurities which also inject controlled amounts of holes. This injects controlled amounts of electrons, whereas an acceptor impurity provides a hole. So, we will discuss this mechanism of how to calculate the carrier concentration, which is the basic information required for technical exploitation of these materials. In order to do this, we will first start considering the energy levels of a donor impurity in an extrinsic semiconductor. This is called an N type semiconductor. So, the fifth electron in a pentavalent impurity is not able to get tetrahedrally bonded to the silicon orbitals. Now, that is because the tetrahedral bonding allows only 4 electrons. So, the fifth electron is loosely bound to the silicon atom. The donor, such as phosphorus or arsenic, is now positively charged because it has donated one electron. this loosely bound fifth electron can be thought of as moving in the neighborhood of this positively charged atom or ion, to be more specific. The dielectric medium in which this motion takes place is that of silicon. So, we consider this in the framework of the well known theory of the hydrogen atom or hydrogen like atoms in quantum mechanics, and borrow the results for this, which is well known. The ground state energy of such a hydrogen like atom is 13.6 electron volts, negative because it is a binding energy, and this is got from the expression minus m e to the power 4 by 2 into 4 pi epsilon naught h square. Now, in this case, the mass of the electron is known to be the effective mass m star in the semiconductor, and epsilon naught is replaced by the relative dielectric constant epsilon r of silicon, and the radius of this orbit of this electron that is the radius is given by and that works out to be 0.53 angstroms in a hydrogen like atom. Now, these things again are modified by the replacement of the dielectric permittivity by epsilon r epsilon naught, where epsilon r is the characteristic relative dielectric constant of silicon, and also the replacement of m, the electronic mass, by the effective mass in the semiconductor. So, the donor energy can therefore be readily calculated using these expressions and using known values of the effective mass and the dielectric constant. So, this works out to be E d, the energy of the donor atom, using the well known result for hydrogen atom, the 13.6 electron volts. This works out to be 20 milli electron volt, which is an extremely small quantity, and the Bohr orbit is also rather large. So, the donor energy levels lie very close, they are very close to the conduction band. So, this is shown in the figure. See, you have the conduction band, the bottom of the conduction band, and the top of the valence band with an energy gap here, and the donor energy band lies very close, donor energy band. It is an extremely small quantity, the distance between them, and the radius of this orbit is also very large. So, there is a big overlap between the orbits of the neighboring ions, and therefore, this forms a donor band. So, this is so close to the bottom of the conduction band that thermal excitation can provide a very convenient way of exciting the electrons from the donor levels into the conduction band, thereby facilitating conduction. So, the fraction of electrons thus excited thermally or otherwise from the donor band to the conduction band is relatively large in comparison to the fraction which is excited across the energy gap from the valence band. So, and these are due to the hole states in the valence band. So, the electrons from the donors are the so called majority carriers, because they are in very large numbers, whereas the holes from the valence band are minority carrier in an n-type semiconductor. By following the same argument, one can also see that the acceptor energy levels lie very close to the top of the valence band. So, this picture is like this. This is the conduction band, this is the valence band, and we have acceptor energy band. Which lies extremely close to the top of the valence band, and because of this we have the majority carriers or holes in this case. While electrons are the minority carriers in a p-type semiconductor. So, this is the overall situation, and now we have already seen that the electron concentration is given as n, and that is 2 into 2 pi m star k b t by h square to the power 3 by 2 exponential E f minus E f. Similarly, the whole concentration is given by a similar expression, where it is the effective mass of the whole, T is the temperature, so the product of these two becomes n times p is considering these two and taking the product of these two expressions, where these are the partition functions which are given by the pre-exponential factors here. Now, the charge neutrality requires that n plus n a minus equals p plus n d plus, where n a is the acceptor atoms which are negatively ionized, and X N D is the donor atoms negatively ionized here, whereas the donor atoms which are positively ionized. This is charge neutrality. Now, N D, the concentration of donor atoms can be written as plus N D plus, and similarly Na is Na0, the neutral acceptor atoms, plus Na minus. Now, it is rather difficult to discuss the general case in which both donors and acceptors are simultaneously present. This can be considered only numerically. We do not want to do the here. We deal with only the case of a donor impurities, which is theoretically easier to deal with in an N type semiconductor. The concentration of donor electrons is Nd 0, substituting for Nd plus, this is Nt by 1 plus exponential Ef minus. Similarly, we can write Pa, a similar expression where Pa 0, we are talking about the ionized impurities which involve only the spacing between the donor level and the bottom of the conduction band and the acceptor level and the top of the valence band. So, with this we can also say that Nd minus is in general very large compared to N. That is, the ionized impurity atom concentration is large. The main contribution to conductivity comes only from this. With that, we can write an expression for N, which is the difference between Nd 0 and Nd minus, and therefore, we can do a little algebraic manipulation to get a closed expression in terms of so that gives the concentration, and which with a little bit of manipulation, again algebraic manipulation, leads to a simple quadratic equation for the concentration. This quadratic equation has the form so for which this quadratic equation can be solved to get a solution for N, which has this form. So, that gives the concentration, and we can discuss in particular three main cases. Case 1, when this quantity under the square root sign is such that 4 N d by N effective exponential E d by k b t. This quantity is very large in comparison to 1, when I can ignore this and write this in terms of, this is the so called carrier freeze out region. Whereas the second case is when this factor is small in comparison to 1, so that this can be neglected and we have a constant concentration. So, this is the saturation region. And then the third case, case 3, is at still higher temperatures. The factor T enters here. The conduction becomes intrinsic. So, the figure shows the 3 regions. One is the intrinsic range as a function of 1 by T, logarithm of the concentration is plotted, and you have an intrinsic range, then the saturation range where the concentration is constant, and then a freeze out range. So, this gives the basic mechanism and basic results of carrier transport in a pure N type of semiconductor, which can be treated analytically. Similarly, a P type semiconductor also can be treated analytically, but as I already said, when both are present, then this cannot be treated analytically, but it has to be done only numerically. We now pass on to consider an important distinction between indirect and direct bandgap semiconductors. These are illustrated in the next figure. In the direct bandgap semiconductor, the conduction band, the bottom of the conduction band So, this is the conduction band, this is the valence band. So, this bottom of the conduction band lies energetically at the same value as the top of the valence band. So, that the band gap is all the energy needed to promote a carrier from the valence band into the conduction band, whereas an indirect band gap is one in which and you have a slightly lower structure here, and whereas we have the valence band here. The conduction band has an energy structure like this. So, the bottom of the conduction band lies here, while the top of the valence band lies here. They do not occur at the same k value. So, one needs to promote a carrier from here to this and then translate it to this by an amount delta k or h cross omega. So, for conduction one has to get a threshold frequency for conduction is just the energy gap for a direct band gap, for a direct band gap semiconductor. For example, gallium arsenide is such a material, whereas in the case of an indirect band gap, we have to have, in an indirect band gap semiconductor such as silicon, one has to have where omega is given by this condition for the wave vector. So, it is because of this that gallium arsenide is a very useful semiconductor in, for example, optoelectronic devices, LEDs, semiconductor lasers and so on. Next, we pass on to a consideration of Hall effect. Hall effect is a very well known phenomenon, especially in semiconductor. So, when a current carrying conductor or semiconductor is placed in a magnetic field, well, let us discuss a semiconductor placed in a magnetic field. So, because of the Lorentz force acting on a moving charge particle in a magnetic field, you get a lateral displacement of the carriers, and therefore, there is a field which is set up in the direction perpendicular to the direction of motion of the charge carriers and the direction of the magnetic field. So, this field is known as the Hall field, and the setting up of this is known as the Hall effect. So, this is in a direction orthogonal to the direction of motion of the carriers and the direction of the magnetic field. So, that is the effect which is known as the classical Hall effect. If you have a conductor with one type of charge carriers, the situation is extremely simple to deal with. Let us consider a configuration which is shown in the figure here, where the field and the current configurations are shown, and one can straight away, using the Lorentz force law, F equals Q V cross B, where V is that of the current, and you have a B direction. So, the force, the lateral force can be readily calculated, and therefore, the Hall field can be calculated. Also, the Hall field is given is if the direction of motion is the x and the B field is along the z direction, the Hall field is directed along the y direction. So, this will be J y B z by n. Let us write q here to denote the charge in a general way. So, this E h by J y B z is known as Hall constant. and that is readily seen to be just 1 by n q. So, this proportionality constant is what is seen here, and therefore, the Hall voltage can straight away be calculated. So, this is the typical experimental configuration for measuring the Hall coefficient, and contacts are made along to pass the current, and a magnetic field is applied perpendicular to the direction of flow of the current, and then the contacts are made also in the third direction to measure the Hall voltage, and this gives the Hall voltage as a function of the applied magnetic field in different values of the magnetic field. The Hall constant is related to the carrier concentration. So, 1 by R h and then q, magnitude of q. So, one can straight away measure the carrier density by measuring the Hall constant, and since the mobility is just, therefore, if we know the electrical conductivity and the concentration, one can determine the mobility as well. So, the Hall effect is used extensively in the measurement of the magnetic field, it is used as a magnetometer, and to measure sign and concentration of charge carriers, and the mobility. These are the important applications of Hall effect measurements.